mutual repulsion. And that's particularly relevant in this particular aspect because we're looking at electron pairs, which remember are negatively charged. Okay, and we know that they're going to repel from one another. So our learning goals are that students will be able to predict the shape of molecules based on shared electrons and lone pairs, and you'll be able to understand the effect of molecular shape on stability and reactivity. So the electrons are important in determining the shape of molecules as well as how they react as well. So we kind of talked a little bit about Coulombs law a little bit earlier when we were talking about different types of bonding, but also whenever we were talking about earlier this year in terms of electrons and where to fill them up. And Coulombs law basically says that we learned that charges want to repel from each other because they are like charged. Electrons are always negatively charged, and because of that, they want to get as far away from each other as they can. Now, the reason why the electrons just don't keep going further and further and further away is there's actually a nice little positive charge in the middle that's kind of pulling them together. So as a result, these charges are attracted in the sense that they want to stay within a certain distance, but at the same time they want to get as far away from each other as they can. This desire, not really desire, but this repulsion between electrons is what determines a molecule's geometry or its shape. And you can see that with Vesper. And you see this is Vesper theory of puppy orbital hybridization. They all want to get to the food, right? They all want to get to the proton, but at the same time, the electrons are as far away from each other as they can, just based on the fact that that's the way that they work in terms of structure. You can't get them to be any closer together. If you move this one over here, it's going to knock this one, which moves this one, which moves this one. So the valence shell electron pair repulsion theory allows you to predict molecular shapes based solely on the valence structure. And it's based on the fact that electrons repel, and bonds are part of that repulsion, and they will move as far away from each other as they possibly can. Okay, lone pairs push away more than a bonded pair, and we'll talk about why in just a little bit. There are some limitations to the Vesper theory, and the first is that the shapes are not always the same depending on the bond length. So, for example, if you have a CH bond, it has a certain bond length. But if you were to take C and you were to bond it with something like, I don't know, iodine, okay, because iodine is so much larger and has a different electronegativity, it doesn't necessarily produce the same bond length, and it can limit the shape. Another limitation of Vesper is it does not work well for transition metals. Okay, transition metals tend to have d orbitals, which are kind of they're delocalized, so the electrons are kind of here and kind of not. So as a result of that, it doesn't work particularly well for those transition metals. Now, example A1 says, explain why an unbonded electrons have a greater bond between angles than bonded electrons. So what it's saying is, this right here has a greater bond angle than this right here. Okay, why is this greater? And if you think about it in terms of Coulomb's law says that you have these electrons that want to get as far away from each other as possible. Well, these electrons that are right here that are represented by these bonds are shared between nitrogen and hydrogen. Yes, it does actually mean that the nitrogen is going to pull these pair a little bit closer than the hydrogen is going to, but it's not a huge amount. And in fact, because they're shared, it's somewhere in between the two. So the pair is probably somewhere in between right here and right here. So because of that, you have this difference in terms of um, how far the electrons are from this central atom. The lone pair is going to be much, much closer to the central atom than these bonded pairs. The distance makes a big difference, though. Because it's so much closer, what this does is it actually provides a little bit more repulsion for these, and it pushes them a little bit further away from the central atom, making these angles tighter and this one a larger angle. It all has to do with Coulomb's law when we're talking about electron configuration and we're talking about shape. So now we want to take a look at some of the most common shapes as seen by Vesper. So the first one is a linear shape, and the linear shape is present whenever you have there are two bonds that repel each other. So the linear shape, you have a central atom and you have two bonds, and when those bonds repel as far away from each other as they can be, the closest that they can be is on the opposite sides. So when you have these opposite sides right here, there is a 180 degrees between the different bonds. And an example of this is something like BeCl2. You tend to see it with things that have two bonds. It's not very common, but at the same time, if you have two things in a central atom, that's when you have a linear atom. Now, a lot of people think that H2O has two things. And they're right, there are two things that are bonded to the oxygen atom, but at the same time, that is going to be slightly different, and that's when we get the bent shape. So you get a bent shape if you have two bonds present, but you also have lone pairs or unbonded electrons. Remember, when you have H2O, you also have these two electrons here and these two electrons here that actually take the shape and they bend it to this particular shape. So the bond angles are slightly different. You have 109.5 between these and 109.5 in between these, while the bond angles between the two atoms themselves is only 104.5. And so examples of these, you have SO2 and you have H2O, with the lone atom, either the sulfur or the oxygen, playing the role of this central atom right here. So that's bent. So you can see the difference between linear and bent is in the configuration of the lone pairs. Next, you have trigonal planar. And a trigonal planar is when you have three bonds that are present, they will repel each other. The bond angles are an equal 120 degrees, 120, 120, 120, and so you get 360 degrees around the circle. An example of it is boron trichloride. In this particular shape is pretty easy to react with because there's nothing in the way for an atom attacking this central atom from above or below. It could be blocked by these around the outside ring of the circle, but it can still get to that central atom. So it is somewhat reactive in the sense that you can still reach that central atom. Next, we have trigonal pyramidal. Just like we had linear, was you have two bonds and then you had lone pairs that could affect it and turn it into bent. You have the same thing with trigonal planar. If you have trigonal planar and then you have a lone pair or two lone pairs, it can actually warp the shape into this kind of bent trigonal planar. You're taking a lone pair right here and kind of depressing the arms of the triangle downward so that it takes this trigonal pyramidal shape. Now the bond angles are slightly different. They're 107 because they've been slightly pushed together due to the lone pair. An example of that would be ammonia. Ammonia has a lone pair on the nitrogen, and so as a result of that, it takes this kind of trigonal pyramidal shape. So next, we've had one bond, we have two bonds, we've had three bonds. Now we're going to have four bonds, and when we have four bonds, we get this shape which is called tetrahedral. Now, once again, this is the shape in which these atoms, because the electrons right here, are getting as far away from each other as they possibly can. If I were to move this atom right here closer to this one, well, then all of a sudden you would have these two that were close together, and this would push this way, and this would push this way. This orientation for tetrahedral is the one in which the atoms can be as far away as possible. An example of this would be methane, where you have carbon as the central atom, and you have hydrogens that surround it. Okay, carbon tends to form a lot of tetrahedral molecules because it forms four bonds relatively easily. Now the bond angles are 109.5 in this tetrahedron because once again, that's the highest that they can go, and be equal. If you were to increase one to 115, it would decrease the other one. You can't do that. So next, if you have five bonds present, you get something called a trigonal bipyramidal. And at this point, people say, but wait a second, if you have five bonds present, you're violating the octet rule. In other words, there are 10 electrons that are surrounding this central atom. And you are in fact right. It is possible to violate the octet rule like we have when we have something called phosphorus pentachloride. So the phosphorus is a little bit further down, and it turns out the further down you go the periodic table, the more likely you are to be able to violate the octet rule. So you have what are called expanded orbitals, which have more room for movement as electrons can kind of move around a little bit and still get kind of close to the atom. So as a result of this, you get something called the trigonal bipyramidal state. Now this is once again kind of confusing because you say, well, wait a second, how come this is the orientation in which the atoms can get the furthest away? You have these 90, 120, and 180 degree bond angles. And yes, it kind of depends on where you look at it. Everything is going to be 90 degrees from one another. So if you look at these central atoms, these are all 90 degrees, and then 90 degrees. And the same thing for this bottom one, 90 degrees, 90 degrees, and then 90 degrees. This 120 angle is for these that are kind of in this circular plane. And then the 180 degrees is from the top to the bottom. So those aren't particularly relevant. Really what you're looking at is the fact that it's 90 degrees between these atoms, the top and the bottom, or excuse me, the top and the planar ones, and the bottom and the planar ones. So you have trigonal bipyramidal, which is when you have 5 bonds that are present. Next, you have 6 bonds that are present, and you have octahedral. And once again, you have the orientation in which these are as far as the electrons can get away from one another. You have top and bottom, and then you have these ones that are in the plane as well. And you have the same 90, 120, and 180 degrees. In fact, you don't have 120. Everything's 90 away from each other with the exception of these 180 degree bonds. So this is the octahedral atom. It's once again one of those violations of the octet rule and has to be something that's lower on the periodic table, something like sulfur hexafluoride. You have lots of other shapes that you can form depending on the relationship between lone pairs and number of bonds. So we've seen the main ones: linear and bent, trigonal planar, and trigonal bipyramidal. You can also get something called a T shape if you have kind of 2 lone pairs that are there, although that is somewhat, it's not as common. You can have a tetrahedral. You can have a tetrahedral that has lone pairs. You can have square planar. But the main ones that we were talking about are going to be still linear, trigonal planar, tetrahedral, trigonal bipyramidal, um, trigonal pyramidal, octahedral. It keeps going further and further and further up. You can have 8 to 9 to 10 bonds to a central atom, depending on how big that central atom is in terms of its electron structure, but you do need to know the main shapes that were covered in this particular presentation. So it says predict the polarity and molecular geometry of CH2Cl2. So the first thing we want to do is kind of draw it out. I'm going to go ahead and pick carbon as my central atom because there's only one of them and because carbon tends to almost always be the central atom. So if I draw carbon in the center, there's a couple of different ways that I can draw this. I'm going to draw just 2 of them, but I'm going to draw the hydrogens here and the chlorines here. And if I draw carbon, or if I draw this particular molecule in this way, it does have polarity because chlorine is more electronegative than hydrogen. It will actually pull the electrons this way. Okay, but I can also draw it this way, in which the atoms kind of go against each other. And when I pull with the chlorine this way, I have an equal pull in the opposite way. Same thing with hydrogen here and hydrogen there. So you can't really predict the polarity based solely on this because it can be either polar or nonpolar. This version is polar. This version is nonpolar. So you don't have enough information to determine the polarity, but you can predict the molecular geometry regardless. There are 4 bonds to the central atom, so you know it's going to be tetrahedral. It says an element has to be part of what chemical family in order to be able to be the central atom of an octahedral molecule. So to be the central atom of an octahedral molecule, it needs to be able to have 6 bonds. And if you have those 6 bonds, okay, you have 1, 2, 3, 4, 5, 6. Now sulfur is the one that was referenced before, but it turns out that it is anything in that oxygen family called the chalcogens. Now the reason why it is the chalcogens is they have 6 valence electrons. In other words, they can share 1 electron to 6 different things. Now, the reason why oxygen, it tends to not work with oxygen because oxygen has its electron shell relatively tight together. But when you start to get into something like sulfur, there's a much bigger distance, and those things tend to be able to share with 6 different things. There's just not enough room to fit all these molecules around oxygen. And the further you go down past sulfur, the more likely it is that it can be the central atom of a of an octahedral molecule. And finally, it says, using the clear method, explain why the molecular geometry of water is bent and not tetrahedral. And the reason is because the lone pairs provide a greater repulsive force, kind of depressing these hydrogens down and making it so the bond angles are not nearly as equal as they would be in a tetrahedral molecule. So our conclusion would be they're not. Okay, our conclusion would be that they're not equivalent. Okay, our evidence would be that H2O has 2 lone pairs. And our reasoning would be the lone pairs provide a greater push, or they push more than bonded electrons. So, you need to be familiar with the molecular shapes that are predicted by Vesper. You need to be able to say, yes, based on this chemical formula, it's going to take this shape, or you need to be able to build these models and see what the central atom is going to look like and see if it's easy or difficult to get to the central atom.